In this lecture, we will further elaborate on the topic of electrostatic shielding. So, in our previous lecture, we have seen that if there is a conductor with a cavity of arbitrary shape and this cavity is empty, that is, it is not carrying any charge. So, in that case, we found that the electric field inside this cavity is zero, and this interior surface of this cavity, this surface is also devoid of any charge. That is, there is no charge on the inside surface of this cavity. This we have found in our previous lecture. And because of this, we have also seen that no matter what I do outside, I put any extra charges or do something, it is not going to matter here, and the field will still remain zero and the charge will still remain zero on the inner surface. So this was how we were going to shield anything from outside electrostatic fields. Now, to see the reciprocal of it, whether this shielding works in other way or not, I told that it will work if this conductor is grounded. Or in a sense, I could have also told that instead of being at grounded, we could have kept it at a constant potential by connecting it to a source. So let us see why we need this ground connection or a constant potential of the conductor. So let us say that this initially, and I will take for the sake of symmetry and easy calculation, a spherical cavity only now, so that we can easily explain. So this Q, let us say I have a charge. So if it is not grounded, what will happen if I bring this charge Q inside the cavity? So it will create a field. As we know that this inside surface will carry minus Q charge distributed over it, and the outside surface will carry plus Q charge distributed over it. And the outside world will think that there is a charge at the center. Means the outside world will come to know that there is something happening inside the cavity. Although it will not know whether the charge is symmetrically placed or not, it will just think that the charge is at the center because of this spherical symmetry. So the field would be easily found out using Gauss law as Q by 4 pi epsilon naught R square AR. That is the radial direction. And you see that because of this field, this conductor will now come at a potential of Q by 4 pi epsilon naught R, where this is the R, okay, outside radius. So if it were not grounded, it would have come to a different potential, and the outside world is going to know that there is a charge inside. Okay. However, if I would have connected it to ground, what would have happened? The ground would have supplied some charge so that the total potential is zero. So Q 4 pi epsilon R plus some charge supplied by the earth 4 pi epsilon R would have given the voltage 0. So the charge supplied by the earth would be minus Q. So because of this, what would have happened? The outside world now will not know whether there is any charge inside or not. I can do anything with this charge, remove it or increase it or keep it at some unsymmetrical position. But the outside world will be totally independent of it. And the electrostatic field on the outside will not change because of the changes which I will make on the charges which are inside this cavity. So you see, this ground connection or a connection to a source to keep it at a constant potential is very necessary to keep the outside world shielded from the charges which are inside the cavity. So this is a very crucial knowledge to keep in mind, because people do mistake and they think that this conductor, even if it is not grounded, can be easily used as a shielding. Okay, now there was a small topic which we had left in our previous chapter or lecture, which was the electric field due to a charged conductor. Let us say this is a conductor which is having plus charges uniformly distributed over the surface. We have taken plus charge just for the sake of definiteness. We could have taken minus charge also. So we want to find the electric field near this surface. So as we know that this surface is equipotential, so field will be perpendicular to this surface. So we will, what we will do, we will make a very small box, rectangular box or pill box, which we usually call it, which is having one surface in the conductor and other surface just above the surface of the conductor and this curved surface. So E dot ds, the Gauss law, if I use, will have components from the top surface, bottom surface, and the curved surface. Now for the curved surface, ds will be in this direction. Okay, so E dot ds for the curved surface will be E ds cos 90 equal to 0, because these both are perpendicular. So this will be 0. For the bottom surface, this field is 0 inside the conductor because it is inside the conductor. And in electrostatics, E is 0 inside a conductor in steady state. So you see, this will also be 0 because E is going to 0. So only thing remaining is E dot ds is equal to, over the top surface, E dot ds. Now if this surface is very close to the surface of the conductor, so this normal as well as the electric field direction will be in the same. So E dot ds will change to E ds cos 0, and I am assuming that this surface area is so small that E is constant, so E ds top. So it comes out to be the E into A, where A is the surface area of this top surface. Now this is equal to the total charge enclosed. Now charge enclosed is just this much. So let us say this sigma s will be the surface charge density. So total charge enclosed will be sigma s into A, and over epsilon is the Gauss law. So E is simply sigma s by epsilon naught, and direction is the normal direction. So in this way, this is the electric field created by a conductor. Now you will wonder that why it is different from a normal infinitely long charged plane sheet, where we found that field is sigma by 2 epsilon naught a and b. So from where this doubling factor has come for a conductor. So we will explain this peculiarity now. Actually, the charges which are very near to the surface are still creating this sigma by 2 epsilon only, the electric field. However, the resultant field is what is sigma by epsilon naught. So let us see how it is happening. So let us say this is the surface of the conductor. Okay, and I am very close to the surface. This is point P1 and this is point P2, and this is the conductor surface. This is inside, this is outside. Now outside we have calculated the total field. Let us say this is EO, the total field. Now I am breaking this outside total field, resultant field, into two parts: E due to the nearby charges and E due to the faraway charges. That is, the charges which are very near to this point P, these charges are going to create some field, and remaining all other charges are going to create some other field. So you see, for point P1, the E near will be in this same direction as E naught, but for point P2, E near will change its direction and it will be in the opposite direction, that is minus AN. If this direction is AN, this direction will be minus AN. Okay. However, for the faraway charges, these faraway charges, this direction is not going to change even for P2 as well as P1, because for faraway charges there is no much difference between P1 and P2, because these are very close. So this E far is still going to be in AN direction. So for the point P2, the resultant field is 0 because it is inside a conductor. So E nearby plus E far is going to give us 0 value. So 0 is equal to, now imagine a scenario that you are very close to a charged surface. So if you are very close, you will think that this charge surface is very large or infinite in you think like an ant which is very close. So you will the ant will think that this world is very large, or you will think that this surface area which is charged is very large. So you will think that it is creating a field of sigma by 2 epsilon naught only, which we have derived in our one of the lectures, the field due to a infinite long charge surface. Okay, but direction will be minus of an, and E far we don't know as of now. So you see E far is simply sigma by 2 epsilon naught an. So the total charge, total field on the outside will be E nearby will now change this direction here. So it will be sigma by 2 epsilon naught an, and E far we have just calculated sigma by 2 epsilon naught an. So in this way we have seen that it is now sigma by epsilon naught an for a charge conducting surface. So you see that the nearby portion of the charge is still creating that sigma by 2 epsilon only, but because of the resultant field we are getting this sigma by epsilon or the doubling factor in the case of a conductor. Now there is a very interesting question, and this question we will see in the next slide. So let us see what is the question. The question is to find the force on the surface of a charged conductor. So you might remember I was telling that the expression for Coulomb's law or Gauss law, they do not consider the self forces of the charge on itself. So now we are trying to find, because there will be so many charges on the surface of the conductor, we are trying to find what is the force on the surface of the conductor because of these charges. Okay, so we have just proved here that the field due to nearby charges, the field due to nearby charges at a place is E is equal to sigma by 2 epsilon naught an, either in this direction or minus an in this direction. Okay, so the force will be the charge in this area and the field. So what will be the charge? Charge is simply sigma into delta S. And what will be the field? At this point, the total this field will be, although resultant field is E naught, but as you remember that this total field is having both expression, the field due to the nearby charges as well as the faraway charges. So for the expression of force we need just the force due to these faraway charges, not the self charges. So the faraway charges were going to create a force of sigma by field of sigma by 2 epsilon naught. So this is the force which will be felt by the charges contained in this surface area. So force per unit area, that is pressure on the surface, is simply sigma square by 2 epsilon. So this is a very important result wherein sometimes if we are required to find the force on the surface of a charged conductor, so this is what is really required to understand. So you should always remember that a charged conductor is always under pressure because of electrostatic forces, but these forces are not that big as compared to other forces, mechanical forces. So we usually do not consider them in calculations because the charge density is very small, and sigma square is already going to be very small if sigma is small. So This is what one of the expressions. Now we will see further that I can convert it to half epsilon naught E square, where this E is the resultant field. Let us see how. Half epsilon naught resultant field was sigma by epsilon naught. So you see, I can write it as sigma square by 2 epsilon naught. So this was the resultant field. So this pressure on the surface of the conductor is sigma square by 2 epsilon naught. It can be written as half epsilon naught the resultant field square, and this is actually equal to the energy density of the field. So this is one of the important results which may be utilized somewhere else, and this force is always trying to stretch the surface of the conductor because all the charges are repelling each other, so they are trying to stretch the surface of the conductor. So in this way you can see that this conductor which is charged is always under tension. So if you find this lecture is helpful to you, then please share and subscribe my YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.